Okay, so welcome to Math383 Complex Analysis. I have this as lecture 30. And so what I want to do today is talk about convergence theorems. And the goal is to avoid doing algebra at the board as much as possible and concentrate on your big picture, what's going on, giving you a sense of what should you expect as a possible theorem, how can you try to prove it, and then I strongly encourage you to go through and put in the details. That's how you know you really understand something, when you can go through and put in the details. All right, so what I want to start with is a theorem that I mentioned last time, which was listed as important, so it must be important, else it wouldn't be listed thus, right? So let A and be an approximation to the identity. That means it's non-negative, it integrates to 1, and as n goes to infinity, the probability of being away from, say, delta from the origin goes to 0 for any fixed delta, that as n gets larger and larger and larger, more and more of the mass is concentrated in a smaller and smaller window about the origin. So when you look at this theorem, as long as I'm assuming f is nice, your continuous function, this is really a no-brainer, right? Of course something like this should be true. It's basically saying, look, if I integrate my function against an of x, as f is bounded, it's uniformly continuous because I'm on a compact interval. So the function f has to be bounded. So once n is really, really large, the probability that I'm away from 0 by more than delta has to become negligibly small. So essentially, I only care about this in an interval from, say, minus delta to delta, where delta is as small as you want. Well, when delta is as small as I want, what can you tell me about the value of f of x for a continuous function? It's basically f of 0. So I'm just integrating f of 0 against a function that integrates to 1. What should you get if you integrate f of 0 against a function that integrates to 1? F of 0, right? So this is really a fairly obvious theorem. You should then go through and do all the details and show that it works. What I want to do is I want to explain that this theorem, the proof we just gave, actually proves a lot more than it looks like we've done. And a lot of this comes from writing things the correct way. So everybody agrees that if an is a family that's an approximation to the identity, then an is a family that's an approximation to the identity. We can all agree on that? No, come on. All right. Well, what about the following? Would you agree that an of negative x is also an approximation to the identity? Yeah, not a big deal, right? It's still going to integrate to 1. It's still going to be non-negative. I'm just flipping things. Not a big deal. So I can consider the following. The integral from minus a half to a half of f of x an of x dx is the same as the integral from minus a half to a half of f of x an of 0 minus x dx. Right? Because, and I'm still integrating against an approximation to the identity. So do I have an equality here? Do I have an equality, yes or no? An has to be even. I do not have an equality. They're basically equivalent, however, as n goes to infinity, right? If I understand the limit of the left-hand side, I understand the limit of the right-hand side. They have the same limit, but for finite n, they don't have to be the same. It's really easy to gloss over small technical points. So they do not have to be the same. They have the same limit as n goes to infinity. Okay, so when you look at this, I have f of x, an of 0 minus x. So when I look at an, what is the input for an where essentially all the mass is in the limit? An at what value do I care about? 0. So when I look at this integral, not surprisingly, the only value of x that really matters is when x equals 0 or when x is extremely close to 0. More generally, I could study the integral from -1/2 to 1/2 f of x an of y minus x dx. I can study this as well. When I look at this, which is the value of x that should matter? Y. It should be the value of x that's near y. Only x near y matters. And we call this f star an of y will be the integral from -1/2 to 1/2, and I'll do this as a definition of f of x an of y minus x dx. And this is the same as the integral from -1/2 to 1/2 of f of y minus x an of x dx. And I can do this by just doing a change of variable. If you let t be y minus x, so here, in fact, I'll use a different letter here. I'll use the letter t. To do this, just let t equal y minus x. So the y minus x becomes a t. X, well, if y minus x is t, then x is going to be, how did I get things wrong? X is going to be y minus t. And that's the other part. So I can just do a simple change of variable. Did I drop a minus sign?
We're still integrating from
for stuff like this, it's often more
if not, we can just switch it to, because we assume f is periodic.
Because we're assuming f is periodic. I'm trying to see, do I assume that f is periodic here? Let's make f periodic. So we'll make it a periodic function. This is why it's often easier to integrate from -infinity to infinity and work with functions like that. We've got to be a little bit careful here that when I have a finite interval in terms of what's going on. So when I look at this, how many of you have seen convolutions in probability? That's essentially what's going on. This is essentially a convolution. This is the definition of a convolution. I'm trying to motivate it by starting off with, I want to integrate f of x against an of x, and that's going to just give me f of 0. What I'm really doing is that's f of x an of 0 minus x, where I'm just looking at a flipped family that's also an approximation to the identity. And that flipped family, I'm doing things at 0. Well, rather than doing things at 0, I could do things at some arbitrary point y. What do you think this should now converge to? F of y. And so instead of showing that equation 11.21 converges to f of 0, we'll show this converges to f of y. Moreover, we'll show not only does it converge, but the convergence is nice. That if I want to be within epsilon, there's going to be some choice of n naught, such as for all n greater than n naught, it'll be within epsilon no matter what value of y is. This is where I'm going to be using uniform continuity and the periodicity. It's sometimes nice to prove things in as much generality as possible. We're going to care about applying this to Fourier series and Fejer series, which are related to Fourier series. They're weighted Fourier series. A lot of times in mathematics, we can write things down. The question is whether or not we can do it in a useful manner. In a real analysis class, you'll see lots of results that are non-constructive. The mean value theorem, there is some point that exists. The intermediate value theorem, there is some point exists. Where is that point? Well, it's between A and B. When you prove the fundamental theorem of calculus, we often use these intermediate points to prove something happens, but we can't write down where they are. Okay? Just because I know this converges to f of y doesn't mean that it converges in a way that's useful. How would I actually compute this in practice? Well, it turns out if I choose my weighted Fourier series, this is going to be coming from the Fejer series, there's a very easy way to calculate these integrals in terms of the Fourier coefficients. which means I can then compute these quantities and I can give you an explicit closed form expression that will converge rapidly. So the theorem is actually true for any approximation to the identity. It's only useful in many situations if we can actually write down what these resulting integrals are. And we'll see later that we can do this for the Fourier kernel. Okay, so let's look at what we're trying to prove. So we will have f is periodic, it's continuous, an is an approximation to the identity. And so let's look at the integral from negative infinity, so negative 1/2 to 1/2 of f of, we said it's the same as y minus x, an of x. And what do you believe this equals? F of y. So I'm going to subtract f of y. And I want to show that this is small. What can I multiply f of y by? I'm sorry? 1, right? I can only multiply it by 1. Does anybody know a good way to represent 1?
Like value of an is 0.
We don't know an of 0 is 1, but you're close. The integral from minus 1/2 to 1/2 of an of x dx equals 1. The area under the curve is 1. So if I just write that 1 as an integral of an, oh, look, I've got 2 integrals involving an. Wonderful. So this is then going to just equal the integral from minus 1/2 to 1/2 f of y minus x minus f of y times an of x dx. And this is where I really hope the proof writes itself because I have no notes on me, right? We want to divide this up into different regions. What would be good regions to divide this into? Okay, so yes.
Why can't you write like f of y into the integral when it's actually outside the
Well, because the f of y is a constant. There's no x dependence. Because there's no x dependence, I can just bring it inside the integral. This is why I was very careful before to say that I can change variables and write it like this. So how do I want to break up this integral?
Delta, where like an is negligible.
Good. So the absolute value of x is less than delta of f of y minus x minus f of y an of x dx plus the integral delta less than the absolute value of x less than 1/2. And if you want to feel good, I'll put less than equal to, it doesn't matter. And I'll have f of y minus x minus f of y an of x dx. So I now have 2 different pieces. Now, because f is continuous, it's not just continuous, it's uniformly continuous. So by uniform continuity, given an epsilon greater than 0, there exists a delta independent of points such that if, say, a minus b is less than delta, that implies f of a minus f of b is less than epsilon over 2. Why do you think I'm saying epsilon over 2? Yes? Because I'm adding the 2 pieces, and at the end of the day, I want to get epsilon, and I want to impress you with my addition. Yes?
Wait, is f assumed to be uniformly continuous?
Nope, f is assumed to be continuous and periodic.
Because
Because it's a closed compact set, any function that's continuous is uniformly continuous. And so if f was not periodic, this would be false. I could have wraparound effects. But yes.
Is that because the derivative is bounded or why?
Oh, I have no derivative here.
So you said.
I'm just a continuous function on a compact set is uniformly continuous. And so f is continuous on a compact set. Yes.
Doesn't AN have a discontinuity at 0? Or is that something different?
Nope, nope. It's just in the limit as n goes to infinity, AN is becoming a delta spike. But for each finite big N, AN is a nice function. It's a sequence of functions. Think of it as a Gaussian. And this is where I like to be able to go and show what we had, I think, before. We had something like this, where I would write it as AN of x was n times some density. And then as I put n over here, once x moves up to the size 1 over n, this is now like f of 1. So if I move a little bit more than 1 over n, if I moved up to like 1 over square root of n, this would be f at square root of n. We would expect the function to be quite small by the time we've moved that far. So I don't expect there to be much value. Now, there could be some small points where the function is quite large. And we'll see an example of that later. But it's not going to integrate to anything sizable because the integral is 1. And it's so that once we move away from delta, as n gets very, very large, the integral becomes negligible. Then we know that the contribution is going to be extremely small whenever I move away. So we will bound that in a moment. Yes.
Sorry, you said something about how f being periodic is required for uniform continuity. It seems like we just get that from the fact that it's continuous.
Well, I've got to be a little bit careful because if f of 0 and f of 1 are not the same value, when I start wrapping around, 0.99999 is close to 0.00001. And so I'm considering the 0.00001 to be very close to the 0.99999. If you want, think of this instead as I'm looking at things on a circle. And here's the point, 0, and maybe here's the 0.2 pi. And I'm going around a circle like that. And so a lot of times we take the interval 0, 1, and we consider it the same as a circle walking around like that. And so when I look at f of y minus x minus f of y, if y equals 1 and x is a small positive number, this is just a little bit less than 1, this is 1, great. But if x is now a positive number, this goes beyond 1. Or if I just consider f to be periodic, then I don't really have to worry about that. These are still going to be very close to each other. And I could view this, if you want, as it's periodic, and I'll just look at it on the interval from, say, minus 10 to 10. I really only care about what's going on from maybe minus 1/2 to 3/2. And then I don't have to worry about any of the wraparound effects. And I can just use it's continuous on that bigger interval and not worry about those edge effects. And so because of continuity and compactness, it's uniformly continuous. I can find for any epsilon a delta such that this is less than epsilon over 2. And so if that's less than epsilon over 2, what would be the value of this whole integral? Can you bound it? So the difference in the functions is at most epsilon over 2. An is non-negative. Yeah, so this would just be, so it contributes the absolute value of the above would be less than equal to, nope, it would be epsilon over 2, the integral x less than equal to delta of an of x dx. And that's just epsilon over 2, at most epsilon over 2. Remember, an is having more and more of its mass concentrated in a smaller and smaller interval. And so when I'm trying to figure out what's the integral of an of x, it could be as large as 1. I don't know it's necessarily going to be small because I'm confining it to be a small integral delta. But that's okay. It's okay that this could be big because I'm going to win out over here. Well, for the first integral, if the difference of f is saving me and allowing me to deal with whatever happens with an, what do you think is going to happen in the second one? I'm sorry?
the integral.
The integral is going to save me. And so now, what can you tell me about f of y minus x minus f of x? That's going to be less than or equal to twice the maximum of f. Right? Because we have a continuous function on a compact set, it attains its maximum. So I can bound f of y minus x minus f of y. It can't be too much. And now I'm left with integrating over all of the x. And so now this is going to be the absolute value of the above will be less than or equal to 2 maximum of the absolute value of f. And then I'm left with the integral delta less than or equal to the absolute value of x less than or equal to 1/2 of an of x dx. So choose n so large that the integral is at most 1 over, let's do epsilon over 2 divided by 2 max absolute value of f plus 1. So why do you think I'm choosing 2 max absolute value of f plus 1? Yes.
Multiply it by max f plus 1 and add it so you get f of x.
Well, I'm multiplying by 2 max absolute value of f, not plus 1. Why am I putting the plus 1 there?
Just to be safe.
Yeah, just to be safe. What if I gave you the 0 function? Right? So always cover your ass. Always make sure you're careful. And this way I don't have to worry about anything. I know that's going to give me a little bit of extra security. And so this piece is going to be at most epsilon half as long as n is sufficiently large. This piece is going to be less than or equal to epsilon halves. That's true for all values of n, so long as delta is sufficiently small. Yes.
It doesn't depend on delta.
So now I just have to put all the different pieces together. And so what I want to do is I want to show that as n goes to infinity, this will be true. And so all I need to do is to just say, how large must delta be? Right? So the second one, it's very easy to figure out how large n must be. For this part, if I want to be within epsilon, I can figure out exactly what delta needs to be. You know, you give me an epsilon, I can find the delta. And I just send n to infinity. And so what I'm now able to do is I'm able to show that this approximation to the identity, the integral that it gives me, is converging to my function. And the convergence is really nice. I can get it so that, you know, when I look at the difference between my approximation and f of y, that difference is at most epsilon if n is sufficiently large. You tell me how close you want to be, I'll give you an n, and once you are larger than that, you're done. And I just have to make sure that, you know, everything is working out over here. Well, you give me an epsilon, I can easily figure out what delta is, because that just depends on f. So I left more blank pages and more blank pages and more blank pages. They're not needed. It's really just a one-page proof. Yes.
So is this convergence uniform convergence?
So this is uniform convergence. You give me any point, and I can show that the difference between what you get from the approximation to the identity and your function is less than epsilon. And now it just comes down to, can you find a good choice of approximation to the identity? Different choices of the approximation for the identity will give you different integrals f of y minus x times a n of x. If I can't relate that to something I can compute, this is just of theoretical use. The fact that I can relate this to Fourier coefficients, which are easy to compute, is what gives me hope that this is worth doing. So I left, you know, a bunch of extra blank pages just in case. It's really a one-page proof, splitting it up into two different regions. The really key idea was multiplying by 1 in a clever way. Is I want to somehow take into account the fact that I have an approximation to the identity. I want to view it as a subtraction problem. This is going to be close where the action happens. And, you know, this is the thing I was thinking about for quite a while. over the last 2 days as to how to present this, is to look at this as not an of x, but an of 0 minus x. And I'm looking at a related family that's also an approximation to the identity. It's a different way of introducing a convolution. But what I'm really doing is I'm starting off with my nice definition like this. And I say, no, I want to view it as with respect to a related. It's almost like taking the complex conjugate in the dot product, looking at a slightly different family. All right, now that I have that, let's try to find some approximations to the identities. And there are two natural ones to try. So remember that we define En of x is e to the 2 pi I n x. And so one possibility is the first is called the Dirichlet series, or the Dirichlet kernel, and the second is the Fourier series Fourier kernel. And so for the first one, I'm just adding up all the ENs from negative big N to big N. And I get the following formula after doing some algebra. And the next one is I'm going to take the Dirichlet kernel for each little n going from 0 to n minus 1. I'm going to add them all together, and I'm going to take the average. In mathematics, when you take averages, it often smooths things out. Averaging is a really good thing to do. It often makes things a lot easier to work with. What do you think might be useful in evaluating these? How might you evaluate these sums? What should we use to evaluate? So we want to evaluate, say, dn of x.
It's like expansion for E.
Not expansion for E.
Geometric series.
Geometric series. What is R? And the reason is the sum, n goes from minus n to n, of e to the 2 pi I n x, is the sum, n goes from minus n to n, of e to the 2 pi I x to the n. It's a geometric series. So if I use that, the first one shouldn't be too bad. And the second one is more work. And this is where it's nice to be the professor. And I will leave the more work as an exercise. All right, play with algebra. Do you think either one of these has a chance in hell of being an approximation to the identity? Or maybe both, or maybe neither. When you look at these, does any of these fill you with hope? Or does any of these make you say, no way in hell? Yes.
I like the second one, the FN.
Okay, good. What's a good property of the second one?
It's always not.
It's non-negative. What about the first one? Yeah, the first one also is. So there's no way the first one can be an approximation to the identity. The second one is at least non-negative. Now, if you start to look at it, as n gets very, very large, the numerator is bounded by 1. So as you start to move x a little bit away, it's going to be very rapidly looking like 1 over n. And if you Taylor expand what's going on near x equals 0, this is sine of u is approximately u. So this would be like n pi x squared over n pi x squared. Yeah, it's going to kind of look like n with modulo some powers of x's and pi's near the origin. It's going to be blowing up near the origin. Oh, okay, so maybe this one does have a lot of its mass. So, Taylor expand near origin, Fn of x greater than equals 0 possible, Dn of x, no chance. Okay. All right. So now, F stands for Fourier, D stands for Dirichlet. These are examples of kernels. And so a lot of times what we do in mathematics is we take a function, we integrate it against another function, and that's going to give me a new function. So really what we have here is we have a function k of two variables, x and y. But it's an extremely nice function. It only depends on the distance from x to y. And so instead of writing this as an arbitrary function, k of x comma y, I'm just writing it as k of x minus y. But k is really a function of two variables. We are looking at a very special series of problems coming from kernels that only depend on the difference of the two variables. And so I can form a new function by integrating a function f against the kernel. And so when I integrate this, I integrate out y, and I'm going to be left with a new function of x. Okay? And so the Feyer and the Dirichlet series, the Feyer and Dirichlet kernels yield new functions. Now, what's really nice is if we look at f convolved with the Dirichlet kernel and evaluate it at x, we will get the sum, n goes from minus n to n, of f hat of n e to the 2 pi I n x. Ha! It's the Fourier series. So if you convolve with the Fourier series, I'm sorry, if you convolve with the Dirichlet kernel, you get the Fourier series. Now, what if you convolve with the Feyer kernel? Would you believe me if I wrote the following? That you also get the Fourier series. Oh, right. You shouldn't get exactly the same thing. Also, there's a space between the sum and the f, so that's kind of a hint that something is coming in there, right? And you get 1 minus the absolute value of n over big N. So these are the weights. So if you look about what's going on, when little n is small relative to big N, 1 minus little n over big N is essentially 1. So it doesn't really change the series that much for small values of n. However, once little n is of comparable size, once little n, say, is big N minus the square root of big N, then all of a sudden, this is going to look like square root of n over n. It's going to be small. So once you get to the end of the finitely many terms that you're looking at, they now have a very small weight, and you're not really contributing that much. So this kind of balances the issues, okay? And this is going to give us much better convergence properties. This is a general theme in mathematics. The more averaging you do, the easier it is to study things. Putting in weights makes things a lot easier. Yes?
Kind of reminds me of like when you Taylor expand.
Yes.
Factorials, the deeper terms are like much less.
Yes. And then as you go deeper and deeper, you would hope that things matter less and less. Now, what's interesting, of course, is as you let big N go to infinity, more and more terms will now contribute because the weights are going to be getting closer and closer to 1. So in the limit for any fixed little n, as big N goes to infinity, the corresponding weight goes to 1. So just have your mind play with that for a little bit. So in the limit, all of the weights are going to 1, but as you go deeper and deeper down, they're still going to be getting smaller and smaller and smaller. All right, so it turns out that the Feyer kernels are an approximation to the identity. So the non-negativity is easy to see. You know, it's clearly non-negative from looking at this. This is just going to clearly be greater than or equal to 0. If I go back and remember that the Feyer kernel comes from averaging the Dirichlet kernels, well, what I can do is I can start writing it piece by piece. I have E0, I have E-1 and E1, I have et cetera, et cetera, et cetera. How many times do I have E0? E0 occurs in every single one of these. I divide by n, so I have it once. E1 and E-1, they occur in everything but the first. So they occur n-1 times. And that's why it's n-1 over n. And so on and so on and so on. So when you expand it out, this makes the integration very easy to do. When I integrate this, what do I get when I integrate E0? 1. And what do I get when I integrate everything else? So this integrates to 1, and all of these integrate to what? They all integrate to 0, right? This is just e to the 2 pi I x, e to the negative 2 pi I x, e to the 2 pi I 2x. They'll all integrate to 0. So when I write it like this, it's not that bad to see that everything integrates to 0, but the first term whose weight is 1. Good luck integrating this directly, right? If you want to feel your oats as to how great of an integrator you are, go for it. I'll give extra credit, integrate that function directly. Maybe there are some trig identities you can use or whatnot to show that this integral is going to equal 1. It's got to be 1. So much of math is about looking at things the right way. Okay, the Dirichlet kernels are not an approximation to the identity, right? I don't really care what they integrate to. I'll leave that as an exercise for you to figure out what they integrate to. You should be able to figure it out by doing a very similar approach.
Well, if the closed form for f and d are this,
I'm saying the closed form of the sine squared over the sine squared. That's going to be hard to integrate directly.
I mean, if they're not useful, then why do we still?
Well, because they are useful for other things. Because if I look at it like this, one of the things that's very useful about this is this is clearly going to be less than or equal to 1 over n sine squared pi x. And so this helps me show that it's an approximation to the identity. That if I look at sine, sine is going to be increasing as I move away from 0. So this is going to be less than or equal to 1 over n sine squared pi delta if the absolute value of x is greater than or equal to delta. And this, shows the integral over the absolute value of x greater than delta of fn of x dx goes to 0. That's why this expression is useful. Because over here now, I know that this numerator is at most 1, the denominator has an n, as long as x is not too close to 0, and I know I'm going to at most 1/2. Well, as I get close to 1/2, that's sine of pi halves, which is 1. It's only making the denominator larger. So the worst case would be is if I chose x to be delta. And so depending on what you need to do, different expressions are useful for different things. So we can pick and choose. I'm going to be with you for this, and then for another property, I'm going to be with someone else. I'm not going to make a commitment to an expansion of the Fourier series. All right. So depending on what I care about, I will work with different expansions of the Fourier series. Okay. But you want to get used to this, that depending on what problem you're studying, different ways of looking at things will be advantageous. Also, we want to show that it's non-negative, right? Clearly, this is non-negative. But if I gave you this sum over here, it's a little bit harder necessarily to see that it's non-negative. Okay. So continuing, here is a beautiful theorem. Let f be a continuous periodic function on 0, 1 instead of -1/2, doesn't really matter. Given an epsilon, there's an n naught, such that for all n greater than n naught, the Fourier series approximation is with an epsilon. How should we prove this? Done. Right. Did already. Done as Fn is an approximation to the identity. Identity. Done. Now, whether or not this is useful, the only reason it's useful is because we know that if you look at f star fn of x, this is the sum, n goes from -n to n of 1 minus the absolute value of n over n, f hat of n e to the 2 pi I n x. So we actually have a nice form for, this is what we're calling Tn of x. If we didn't have the series expansion on the right-hand side, it would be a different story. But because we have this expansion, we now know that the Fourier series converges uniformly to a continuous function. Unfortunately, not every function is continuous, but if you go further in mathematics, you learn, well, okay, maybe every function isn't continuous, but most functions are actually close to continuous functions. Most functions are close to continuously differentiable functions and stuff like that.
Sorry, can you just go back to the slide?
Yep. So we're basically just saying we have uniform convergence because we have an approximation to the identity. This is just the previous theorem where instead of writing an, I'm writing tn. And tn is just coming from looking at the integral of f convolved with the Fourier kernel.
Is there a typo where it says Tn fx goes to fx? Or is that correct?
At the very end?
Yeah, should that be the Fourier kernel fx?
Well, no, because tn of fx, this is basically f convolved with the Fourier kernel at x.
Right.
And so I'm just calling that tn of x. So tn is not the approximation to the identity. It's fn that's the approximation to the identity. And I'm calling the resulting function tn. That's what we were calling before f of y minus x times an of x dx and doing that integral. So the only reason this is useful is because this integral, the f star fn, which is what I'm calling tn of x, is I have a nice expansion for that. If I didn't have a nice expansion for that, this would be useless. Okay. Now, it turns out you can prove a lot of things from what we've just done. I'm not going to go through this due to time constraints. I'll let you read later and think about how you can deduce all these theorems from what we've just done. Okay, so you have a lot of wonderful approximation theorems. If you don't want to approximate with weighted Fourier series, you can actually use this to deduce that you can approximate with trigonometric polynomials in terms of sines and cosines. Or if you want, just in terms of regular polynomials, just Taylor expand your sines and cosines, and then just keep track of the errors. So there's a tremendous amount of approximations you can now do from all of this. Okay, now let's turn to the Fourier series. We don't want to do weighted Fourier series. It would be much nicer not to have to put in this fact of 1 minus absolute value of n over big N. So what if you remove those weights? Well, the theorem is no longer necessarily true. But it is true if your function f has some additional good properties. And the general rule is the more differentiable you are, the better convergence you have. Has anybody here heard of Lipschitz properties of a function being Lipschitz? Fine. If you've heard Lipschitz, you can replace differentiability with a Lipschitz condition, and that would give you similar results. I just need a boundedness of the first derivative quotient. So if that means anything to you, that's great. If it doesn't, it gives you an inspiration to either go to the internet and search, to ask me, or to take even more analysis classes. Differentiability is a little bit stronger than I need, but it's met in many situations. So now, if we take a real valued periodic continuous function that's bounded and differentiable, then we have pointwise convergence of the Fourier series to our function. And here, Sn of x is just f convolved with the Dirichlet kernel at x. So this is saying the pointwise convergence of the Fourier series occurs. It's extremely important that the function is differentiable. You might notice I never said my function f is continuous. Why didn't I mention that f is continuous? Yeah, it's implied, it's differentiable. So do I actually even need to say that the absolute value is bounded? No, because it's differentiable, it has to be continuous. Because it's continuous on a compact set, it has to be bounded. So I don't know why I chose to be explicit about boundedness, but not continuity. Probably just to emphasize the point. All right. Here is the proof. I don't want to go through the proof in detail. I want to just highlight at a high level what's going on. We start off very similar, except this time I guess I'm switching the order in which I write things. Just mixing it up a little bit. So again, I use the fact that the integral equals 1, and then I subtract, and then I put in my expansion for dn. And when I put in the expansion for dn, I move one of the factors over, the sine pi x into the denominator. Well, when x is really close to 0, what does sine of pi x look like? It looks like pi x, right? So this is really, f of x naught minus f of x naught minus x. X is my small little h. This is looking like the derivative. It's the quotient that's converging to the derivative. And so if my function is differentiable, eventually this quotient has to be within f prime of x naught by a small amount. And that's essentially what's going on, is that this quotient has to be bounded and it can't explode. So the problem with the Dirichlet kernel is we've got this sine pi of x in the denominator, which can blow up. But because of the differentiability of f, I can handle that. And I can have this new function g that's bounded. I'm integrating it against sine 2n plus 1. Well, integrating against sine 2n plus 1, that's the same if you look at the very bottom equation 42. It's just taking the imaginary part of integrating this against an exponential. And then this is where we use the Riemann-Lebesgue lemma that the Fourier coefficients tend to 0. And this came from Bessel's inequality. So if you have stuff like that, you then get differentiability, implies point-wise convergence of the Fourier series. So again, go through the proof slowly, go through all the steps. These were the key ideas. I can take the blow up of the denominator and move it into the difference quotient of the function. And that gives me a new function that is essentially only a problem when x is close to 0. But when x is close to 0, that's essentially the definition of the derivative of f at x naught, which exists by assumption. And so I know that's going to be fine. And then what I'm left with is the very, 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 is the imaginary part of a very large Fourier coefficient as n is going to infinity. And since the Fourier coefficients go to 0, the imaginary parts go to 0. So this has to go to 0. So things have to converge. That's the high level proof of what's going on. Okay, you can then prove a lot of additional items. The big one that we're going to prove in the next class is Poisson summation. We're not going to get to that today, but it's worth just mentioning some results that we have. So you can prove Parseval's identity, that the sum of f hat n squared is the integral from 0 to 1 of the absolute value of f squared. We also have often, point-wise convergence. You could actually use this to evaluate lots of sums. And so one of the nice applications of Fourier series like this is I can actually evaluate the sum of the odds, 1 over 2n plus 1 squared, by choosing an appropriate function. Once you know that as a nice exercise, deduce the value of 1 over n squared. So I will leave that, if anyone is interested, by all means, try to do problems like this. One of the difficulties is to figure out what function to use. One possibility is try a bunch of functions, see what gives you a nice answer, throw away everything except for the one that gives you a nice answer, and then present to the world the nice function. Yes?
Wait, since we know that like Tn converges to f uniformly,
Yes.
how do we need to also look at S? Because S.
Well, the problem is we often want to look at not weighted sums, but just the sums of the Fourier coefficients. And the Fejer convergence, we have those weights. And the weight in front of f hat of n changes as n gets larger and larger and larger. As we let big N go to infinity, the weight in front of the coefficient 1 or 2 or 3 or 4 or -5 is changing. It would be wonderful if you take Taylor series, as you take more and more terms in the Taylor series, it doesn't change the previous terms. The previous terms have stabilized. You're just adding more terms to your expansion. With the weighted Fejer series, the more terms you take, unfortunately, the more you've changed things in the beginning. Now, eventually, these weights are getting so close to 1 that you're really not changing anything. But you technically have variability as you're going. The Taylor series is very different, because you're just adding new pieces. And so we can use this to evaluate lots of nice things. We've still got a little bit of time. So the Fourier transform is defined as the integral of f of x times e to the -2 pi I xy. For any physicists here, I apologize about the sheer number of different ways of normalizing the Fourier transform. You can either have the 2 pi or not the 2 pi. In the exponential, you can have the minus sign or not. You can sometimes have a 1 over square root of 2 pi outside. You can try to have multiple of these things and try to either appease everybody or piss off everybody, depending on which way you want to view things. Just be careful whenever you look at a book that you know how they normalize things. If you're an engineer, what would you have rather than I? J. So the engineers use J for the square root of -1 because I is for current. Okay, so this is the Fourier transform. And the last thing today is the Schwartz space is the space of all infinitely differentiable functions whose derivatives are rapidly decaying. What do I mean by rapidly decaying? I mean, you take any polynomial that's never, so I'm going to look at absolute value of x plus 1, so this is never 0. I raise that to the jth power for any j. And I take any number of derivatives of my function. And then that's going to be bounded. Well, if that's bounded, if I just take J to be a little bit larger, if that's still bounded, this means this has to be decaying faster than 1 over polynomials to any power I want. Can anybody give me a function that they think should be in the Schwartz space? It and all of its derivatives. So e to the negative. That will not be Schwartz or negative infinity to infinity. Negative x squared. Because if you have negative x, if x is negative, it becomes positive.
Oh,
And here's another nice one. E to the negative 1 over x minus a, b minus x, a less than equal to x less than equal to b, and 0 otherwise. This function is going to be basically decaying extremely rapidly at a and b, and then is 0 everywhere else. So this is a strange function which is infinitely differentiable. It's a good function to know. And so the deeper you go in mathematics, the more you start collecting examples like this. All right, this is a good place to stop, and then we will continue with Fourier series on Friday.